we will tell you a little bit about our paper, an Euler totient sum inequality. The motivation for this work comes from the theory of power graphs of finite groups. The power graph of a finite group G takes as its vertex set the group itself, and there is an undirected edge joining each element of the group with all of its powers other than the element itself. So there are no loops in a power graph. A clique in a graph is simply a set of mutually adjacent vertices. The clique number of a graph is the size of the largest clique. We will use chi to denote clique numbers. It turns out that in the power graph of a finite cyclic group, the largest clique is formed by taking the generators of the group, after all, everything is a power of the generators, together with the largest clique of the largest subgroup. Consequently, the clique number of the cyclic group of order n is computed by taking the Euler totient of n and adding the clique number of the cyclic group of order n over p, where p is the least prime factor of n. In the power graph of any finite group G, every clique generates a cyclic subgroup. Therefore, the clique number of the power graph of a finite group G is given by the clique number of the power graph of some cyclic subgroup. It is a matter of finding the appropriate element and applying the results of the previous slide. It was conjectured that the element to take to get the largest clique is the element of largest order. The conjecture fails for the general linear group of order 2 over the field of order p. This group contains elements of order p squared minus 1 and p squared minus p. Manfang observed that the clique number of the cyclic group of order p squared minus p exceeds the clique number of the cyclic group of order p squared minus 1. They did this computationally for primes between 11 and 97. In this paper, we show that this inequality holds for all primes greater than or equal to 11. With the motivation above, we define the clique number of a number recursively by saying that the clique number of 1 is 1, and the clique number of any larger number is the totient of the number plus the clique number of that number divided by its least prime factor. This matches with our formula for the clique number of the cyclic group of order n. As noted earlier, our main result is to show that for all primes p greater than or equal to 11, the clique number of p squared minus p is greater than the clique number of p squared minus 1. The argument breaks down into 3 cases. The first is where the clique number of p plus 1 is p plus 1. This only occurs when p is percent. The case when the clique number of p plus 1 is p. This only occurs when p plus 1 is twice an odd prime. And then the general case where the clique number of p plus 1 is less than p. The arguments are essentially inductive in nature. The argument relies on 3 results, each of which reflect the properties of the Euler totient. The first is that if n is the product of d times L and the prime factors of d exceed the prime factors of L, then the clique number of n is the Euler totient of d times the clique number of L minus 1 plus the clique number of d. This follows from the multiplicative properties of the totient function. Next, if n is the product of d times L, then the clique number of n is at least the clique number of d with equality precisely when n equals d. Finally, for coprime numbers d and L, and in the first lemma we do have coprime numbers, the clique number of the product is at most the product of the clique numbers, with equality precisely when one of these is 1. These 3 properties are actually quite interesting in their own right and suggest that the clique number is a very nice function. We invite the reader to learn more in our paper. Thank you.